Good afternoon.
Oh, yeah, it's time.
Good afternoon and welcome to the Emeritus Professorial Lecture. It's my pleasure to be here with you to honor John Wierman, Professor Emeritus in the Department of Applied Mathematics and Statistics. John is an expert in the fields of probability, stochastic processes, statistics, discrete mathematics, percolation theory, and random graphs. We're here to honor John, but I am personally honored to lead this celebration of my colleague, chair, co-author, co-instructor, and above all, personal friend. John's had an impressive career. Not only has he researched percolation theory and how it applies to lattice graphs, he is a strong mentor of undergraduate research, and he has previously served as chair of our department. He's been the founder and director of the Johns Hopkins W.P. Carey Entrepreneurship and Management Program, which grew to become the Center for Leadership Education. Additionally, he provides spot-on accurate enrollment predictions for the Johns Hopkins Undergraduate Admissions Office and serves as a faculty advisor for the Hopkins women's soccer team. And now it is my pleasure to introduce Fadil Santosa, the Yu Wu and Chow Mei Chen Department Head and Professor of Applied Mathematics and Statistics. Fadil.
My job here today is to introduce the introducer of your talk, and it's going to be online. So I'm just going to say a few words about Davar. Davar was a student, got his PhD here at, he received his PhD at UC Berkeley, but he was an undergraduate here. And then he went to join the faculty of MIT and then University of Washington before settling down for where he is now at the University of Utah. He was, he has been very active in the math community and also not only in research, but also in leadership in the profession. He was elected fellow of the American Math Society in 2020, and in 2015 he was a fellow of Institute of Mathematics, Institute of Mathematical Statistics, IMS. And he was also an IMS medallion lecturer in 2018. So what I'm going to do now is going to push the button and you will be able to see.
Hello and greetings from Salt Lake City, Utah. My name is Davar Krishnavisan. I'm a professor and chair of mathematics at the University of Utah. I'm also a member of class of 1984 at Johns Hopkins. My first interaction with the Department of Mathematical Sciences was through a very advanced course while I was at Hopkins, taught by Professor Wierman. Not only is he a fantastic mathematician, of course, but he was truly an inspiring teacher. I almost went around like a groupie taking courses from him after that. And I ended up studying in the same field and working in the same field that he has contributed to multiple times and in very important directions. John was also my undergraduate advisor, and I can tell you from my personal experience and professional experience since, one of the very best advisors I've ever seen. He was inspiring, patient, with fantastic guidance and guidelines that still serve me today. So I think I'll let you hear the great man himself and introduce him to you next. Suffice it to say, it really, truly is a huge honor for me to be allowed to take part in this very important celebration. Thank you. John, I look forward to seeing you very soon in some meeting somewhere on the planet. Bye-bye.
John, the floor is yours.
Press the right button. Okay, thank Davar for the very kind introduction. I would have to say that of all of the undergraduates that I've taught, he has been the most successful academically, so I'm very proud to have not screwed him up any more than I did. He may also not know or be aware of how much that he was a victim of some practice that we had in those days where a faculty member would often teach a course in order to learn the material. I had never had a course in advanced stochastic processes, And so I was doing what many of us did at the time, was teach the course and try to stay a week or two ahead of this class. But I think that was a very successful model in the way it worked out, because it meant that everything that I had struggled with, I made sure that I explained it as carefully as possible. And so it was really sort of a partnership of the students and I were really learning together. And I think that if I'd taught the course 5 times before, I wouldn't have understood what the students were having trouble with. I wouldn't have remembered as much. So I thought that was a successful model, and evidently it was inspiring to him, so that's great. Okay, so this is only the second of these Emeritus Professor lectures. So I had one example. I really enjoyed Rao Kasaraju's from computer science last spring. And so he gave an overview of his background and his career, research career. And so I have sort of modeled mine on his. However, I'm sure it's sufficiently different that he has plausible deniability and can disavow any claim to that. So the title, Random Walk Through Mathematics and Life at Hopkins, reflects that I am interested in a lot of things. I've worked in more than a dozen different research topics because I'm more of a problem solver rather than a theory builder that sticks to one thing. And the same applies to my other activities at Hopkins. But there really are some themes that are behind it. One is that my main field is probability in random processes, so a random walk is appropriate. But for most people, it looks like the things that I worked on are just a random collection. But there are these themes. One is that everything essentially involves probability or stochastic processes. And the other is that I've done a lot to try to prepare students for careers, both in academia and in industry. Let me see if I can get used to this. Okay, so here's this kind of a strange outline. I thought I'd make it interesting. So instead of saying background and percolation and such, I'm going to tell you many, many stories. I'm limited to I've picked 3 of the most important areas that have nice stories to them to tell you. But a lot of you can visit me later at other times and hear more stories, and some of them that the deans shouldn't hear about. So I'm going to talk about my background, and then percolation theory and use statistics and percolation and random graphs, and then about undergraduate research, very briefly things about other things I did, some of which was mentioned by Ed about the service activities. And hopefully I'll do this in the 40 minutes or so that I'm supposed to. Depends on how fast I get into the flow and when I get off track. But I'm really a person who's more of a problem solver than a theory builder. And so I do enjoy working on a lot of things. On a spectrum of a joke that I heard long ago, I'm in the middle of the spectrum. The joke is that the pure mathematician wants to know more and more about less and less until finally he knows everything about nothing, while the applied mathematician wants to know less and less about more and more until finally he knows nothing about everything. But I was trained as a pure mathematician, but I work on problems, so I'm pretty much in the middle, I think. Okay, so this is what passes for a plan. And so let's get to the background. Why did I become a mathematics professor? The short answer is I wanted to avoid hard labor, but I should elaborate on that. The Wierman family just did not really have very good opportunities for education. And my parents emphasized the importance of education and demonstrated that they valued it. My grandfather Wierman could not read or write. My dad had to drop out of 9th grade during the Depression to join the Civilian Conservation Corps and build trails and fight forest fires in the Olympic National Park in Washington State. My mom dropped out of high school to marry my dad, but then she finished high school shortly after at a different high school. My dad almost single-handedly built a house so we could move to the best school district in the area. And then my mom, after raising 3 kids up to junior high school, went to college, and she became a teacher. So the value of education and teaching was drilled into me in many ways. Oh, let's see. I'm sure there was something else I was going to say. But anyway, so my dad also, when I was growing up, I split wood and dug ditches and so on, and he kept telling me, if you don't get a good education, you'll do this for the rest of your life. So I worked hard during the summers and essentially paid all my way through college by being a migrant worker in Eastern Washington, picking cherries and peaches and pears and apples. I could make about $10 a day, and that was enough to actually pay for the state university and state tuition and such. So why mathematics? Well, I was just always interested in mathematical types of things. When I was a kid, I liked puzzles, dice games, card games. In high school, I developed a system where I could keep reliable statistics for the basketball team. And my high school math teacher and track coach was actually a philosophy major, and he taught us about proofs and emphasized proofs. And that taught me that there was a lot more interesting things about mathematics than just calculations. And so it was very natural at that point to become a math and statistics major. Okay, so let's go to the first story. The title, the unpublished paper that got me hired at Hopkins, this is really about statistics, unbiased statistics. So my first published paper was on the Berry-Sean theorem. It wasn't the Berry-Sean theorem because it proved what's expected to be, the standard result requires a third moment, and with one of my 3 thesis advisors, because I was working on multiple things even when I was a dissertation student, proved the result with fourth one. But the reason for showing this is that there are 2 important names here. Bickel, a lot of the people know here because we still use for statistical theory course the book by Bickel and Doxam, the classic book. And so it was nice to have improved the result of his. And Surfline, the old guys here will recognize that name, and that'll play a much bigger part of the story later on. So this was one of the 3 topics on my dissertation, and my first actual paper published in one of the top journals in probability. And so the idea, so I need to explain what a Berry-Sean theorem and what a U statistic is. U stands for unbiased. A U statistic is, well, you take a sample of observations, sample of random variables, and a lot of statistics, common thing to do is average the values to get an estimate of the mean. Well, what we want to do is generalize that. We want a symmetric function it can be of 2 variables, is how I explained here, but it could be any number. But for a symmetric function of 2 variables, you take every pair and evaluate the function for that pair of observations, and you average those. And so you're averaging dependent random variables, which is much harder to deal with theoretically. But there is a central limit theorem for these, where you get a limiting normal distribution. But a Berry-Sean theorem is a theorem in probability theory and mathematical statistics that basically keeps the central limit theorem honest by telling you how much error there can be. So here, a little bit of notation that sigma squared n is the variance of the U statistic, and the expectation of h over a single pair is mu, and that would be the unknown quantity that we're trying to estimate. And the U statistic will be an unbiased estimate for that, and sigma squared will be the variance of one of these evaluations of h. And if you do if you do the standardization of the U statistic by subtracting off the mean and dividing by its variance, then its distribution function has a maximum distance from the normal distribution function that's some constant over square root of n. And that's considered to be the right rate for the Berry-Seen theorem. And it involves a third moment. This is called a third moment theorem. That's the right condition for generally for the Berry-Seen theorems. Bickel had proved, he'd gotten that rate, the 1 over square root of n rate, when the kernel is bounded, which is a very strong condition. And with my advisor, Y.K. Chan, we proved that we could get that rate with the fourth moment, which is not quite the Berry-Seen theorem we wanted, and as you might have seen in the abstract, that if we had the third moment, that then there would be a log n in the numerator, so we didn't quite get it. But then the reason this next one's in red is that a couple years later, I actually solved the problem to get the third moment condition to get that. But that paper wasn't accepted. And it turned out, when I submitted it, I got an answer back very quickly, like within a couple of weeks, that someone else had scooped me, had gotten the result sent it to the same journal about 3 weeks before, and it had been accepted. The proof was rather similar, but the referee that was referee for both of them liked mine slightly better, but it wasn't enough different to publish the paper. And what turned out was that later on, when I applied to Hopkins was just recreating the engineering school, and they were bringing in Bob Surfling as the new chairman of the department. And he told me after I was hired that he was the referee, and he felt really sorry about having to reject the paper, and that in the hiring process, he had added that paper to my CV and told everybody in the department that that was the reason they should hire me. So he was a wonderful mentor for me while I was here too. But I attribute to him the fact that I actually got hired at Hopkins. Okay, so second story, why work on an impossible problem? Well, this is about percolation theory. And I came across percolation theory in the late 1970s. I was working on my dissertation, and there had been some really famous probabilists that had tried working on it in the late 1950s and early 1960s who had said that they weren't making any progress at all, and they said it was an intractable, impossible problem. Can't make any progress on this. And that's what I was told by several of the faculty members at the time in the University of Washington in my graduate program. But there was one senior professor, Ron Pike, who said, well, if you like the problem, keep thinking about it. Don't bet your career on it. But if it really is impossible, there are advantages. Nobody's going to scoop you and put you out of business. You can't put yourself out of business. But because all of these famous people have tried it, any minuscule progress that you make is going to look very good. And so it's the one problem I've kept working on and through my whole career, and I think I have over 100 papers on it. So it's worked out pretty well to work on the impossible problem. So let me tell you a little bit about what it is and some of the accomplishments. So here is I'll just talk about the very simplest thing and very limited, but a site percolation model is we have some underlying graph that could represent an atomic lattice or an orchard or a population of some kind. We retain the vertices from this underlying graph, infinite graph, at random independently with probability p, and we call the vertices that are retained, which are in red, open, and we can think of them as trees that have disease or molecules that are conductors or whatever. And if they're neighbors, then they can spread the disease or fluid can flow between them or whatever if they're both open. So, and I've got two pictures here with different probabilities of P, and you can kind of see a qualitative difference between them. There are also bond percolation models, which are the edges are randomized. And it turns out actually that bond percolation models are easy to work with and there are more solutions than site percolation. But the physicists and engineers that have been interested in this are more interested in site models in general. The key thing is the percolation threshold, which is a threshold between finite clusters and infinite clusters, which could be like, if you're thinking of bonds being there because of the temperature if you have high temperature, the probability of a bond is low, so you get finite clusters. But if the temperature is low, which is like a liquid because they can move relative to each other, or if the probability of a bond is high, then you have structure that permeates the medium, so it's like a solid. And so there's a phase transition point is what the percolation theory, percolation threshold represents. And that's the main interpretation. There's all sorts of applications, thousands of articles each year. When I started, there were about 5 articles each year on percolation, but there are thousands each year now in the physics and engineering literature, particularly in physics. So I published about 1/3 of my papers in physics journals, even though I've only had 2/4 of physics in college. So my obsession, my Moby Dick, has been trying to prove as much as I can about bond percolation thresholds. And physicists do a lot of simulations, and they give values to 6 decimal places. But if you look at 5 different papers, the confidence intervals don't overlap. The value depends very much on it's very individual for each lattice, but we don't really understand what controls it. But my focus has been, as a mathematician, to find exact solutions if possible. And depending on how you count things, more of the exact solutions are mine than anybody else's. And nearly all the rigorous bounds that are the best bounds right now are mine. But they're not very good. The typical range between an upper bound and a lower bound is around 1/10 to 2/10, with the site percolation threshold bounds being closer to 0.2 and the bond percolation ones being more in a little bit smaller. And it's much worse for 3-dimensional lattices. Although I have gotten, in some cases, I've gotten bounds where the upper and lower bounds agree on the first 3 decimal places, and proved that a conjecture by a physicist by using a heuristic argument was incorrect. He conjectured an exact value, and it was too small. So I will just talk about the 3 most common lattices, which actually have most of the exact solutions. But there are much broader classes of lattices that are interesting. So the square lattice, triangular lattice, and hexagonal lattice. Percolation was introduced in the late 1950s. The first solution was for the bond percolation threshold of the square lattice was 1/2. This was by Harry Keston, very famous probabilist. And I was able to prove the values that you couldn't guess. They were for the triangular and hexagonal lattice in 1981. And people at other universities at the time told me, well, that's going to get you immediate tenure. But of course it didn't. This is Hopkins. I didn't get tenure for 6 years later. The interesting thing about it was there was a heuristic argument that derived those values in 1964, but nobody could prove it until I did in 1981. And that's sort of typical of the field, that they're hard problems. They're easy to state and understand, but they're very hard to make progress on. And then site problems are harder. The triangular lattice is 1/2. That's also Keston, with the same idea. For those of you who know graph theory, it's related to graph duality and self-dual graphs. But for site models, it's something called self-matching. But the bounds are, for site models, are pretty good here. This is about 0.1, and that's a little bit smaller than 0.1 between the bounds. The reason that they're in red, or that in the last 2 years, those bounds have been improved. The site percolation threshold for the square lattice is joint work with a junior, Sam Oberle, that some of you may know, that from last year, and that's the first improvement since 1995. And I did the work on the hexagonal lattice just myself without any student, and that's the first improvement since 1981. So, but that's my industry. There are classes called Archimedean lattices and so on and Lave's lattices that appear in crystallography and so on, where the physicists and so on are interested in these, and trying to find the best balance as I can for as many of them as possible. And it's a good source of it's a good playground for undergraduate students because I can teach them some methods, but it takes some creativity to find ways of comparing lattices to get these bounds, and they can pick a lattice and have some ownership in the problem and devote a lot of time to it. Okay, and so I won't say much about the methods, but I call it finding two needles in a haystack is one way of looking at it. That really you look at finite regions of the unsolved lattice that you're studying and a solved lattice, and you look at the probabilities of connections between the vertices, and you get a bunch of equations from that, and it turns out that the largest solution is the upper bound and the smallest solution is the lower bound. But for the ones that I did recently, the number of equations, if you just follow the definitions, is a very crude lower bound is 2 to the 42,525 power, which is just absolutely impossible. So you have to be smart about it and prove that you can throw away large sections of the haystack. And so in each case, we reduced it down to either around 4,000 or 8,000, and we could solve do all the calculations in a couple of days on a personal computer. So we're always looking for ways to eliminate more so we can do larger regions is the idea. Okay, and there are other flavors of percolation. I've worked in first passage percolation where you put travel times on the edges, and three others I've done a lot of work on as well. Okay, so this is the third story for research story, is what is my Erdos number? I think a lot of you have known about the Erdos number, but since some people, my sister, who I think is online, may not know. This is about random graphs. And random graphs percolation is a specific type of random graph where you take an underlying lattice which has a regular periodic structure, but you can take any graph of points and lines and decide to keep each line, each bond with probability P. And there are many applications of it to these general random graphs. There's many books and hundreds, thousands of papers on it now. And the currently popular applications are to social networks and epidemic modeling. A lot of people the statisticians in the department, Carey Preeb's group, do a lot of things with social networks. And so I'll talk about, the story is about social network relating to this. So, and what is the Erdos number? Well, you need to know about Erdos if you don't already. He's a prolific Hungarian mathematician who worked in almost every area of mathematics. Was a roving mathematician. He never really stayed in one place with a faculty position. And he was a co-author over 1,500 papers with over 500 co-authors. And he's famous for posing problems and conjectures and offering little monetary prizes. And since it was so famous to solve one of his problems, his conjectures, that a lot of people didn't cash them, they would frame them and said, so he didn't really have to pay them out. And he was the co-author of the seminal paper that started the industry of random graphs in 1960, called On the Evolution of Random Graphs. And I called it it's really the mathematics collaboration graph, but usually it's talked about in relation to Erdos, that the social network of authorship connections, where each person is a vertex, and if the two people have written a paper together, co-authored a paper, then there's an edge between them. And your Erdos number is the distance from Erdos. So if you've written a paper with Erdos, your Erdos number is 1. If you've written a paper if you haven't written a paper with Erdos, but have written with someone who did, then your Erdos number is 2, and so on. And mathematicians generally prize having a low Erdos number. So I have a particular version of the a portion of the collaboration graph that I like because it looks more organic with the curved lines and so on. It gives the names, even though my name isn't on it. But Erdos is in the middle. I get to use this. And just to bother Jim Phil, I'll do the swirling, which he hates. But this is just a small part because there are not even 500 people on this. But it shows a lot of things. The person who did this was obviously a discrete mathematician. It's pretty much limited to discrete mathematicians. And just as a side note, another reason that I like this is because if you've ever wondered about the connection between mathematics and hell, this right here is hell. There's a discrete mathematician at University of British Columbia named Pavel Hell, and he rents out his basement to graduate students in the department at times. And so I was at one talk where a young lady that just got her PhD said that this was work that was done in her dissertation, which was written in hell's basement. And I think a lot of PhD students can probably relate to that. So my Erdos number is 2. There's a multiplicity of 3. I have 3 co-authors, Bela Bolabash, Boris Patel, and Tomasz Wuczak that have co-authored papers with Erdos. But that can't be the end of the story because there's a lot of blank space here, right? One of my Swedish collaborators claims that my number should be -1. She just calculates it a different way. Tomasz Wuczak and I proved that one of the theorems in Erdos and Rennie's original article on random graphs is incorrect. Not just that the proof was wrong, the result is incorrect, the theorem. And that theorem was used to prove some major things about when is a random graph, the threshold between planarity and non-planarity, and also the threshold between chromatic number 3 and smaller. And the theorem involved having counting the number of structures with a cycle with d diagonals in it. And so this would be, it has, I guess, 7 diagonals, if I counted right there. So it was about counting that. And it was a very complicated theorem. And I couldn't understand it. And Thomas kept telling me that it was, it's easy, just think about it overnight. I was on a National Academy of Sciences visit in Poland for half the summer. But anyway, can I go back? So one of my Swedish collaborators claimed that my number is -1 because -1 Erdos theorem. So here is the theorem that was wrong. It was well into the paper, and it's slightly different because there are 2 models of random graphs. One is you have n vertices and you choose a certain number of edges at random to be open, as I'll call it. And the other one is you think of each edge being open with a certain probability. N over 2 would correspond to being p equals 1 over n, 1 over the number of vertices. But they wrote this, but they're equivalent models, essentially. There's strong equivalence. And so this was about when you have a slightly above n over 2 edges in your random graph, that the limit of the probability that there's j cycles that have d diagonals in them is this Poisson distribution, and the parameter is this nice little expression, the mean of the Poisson distribution. But it turns out that the correct limit for the probability is 0. For no matter what d is, the number of diagonals. And that you don't start getting them until you replace the square root of n with an n to the 2/3 power. And we proved that this theorem was wrong, and then we proved that we found ways around it to prove the planarity threshold and the chromatic number result anyway. This was done in 1985 in the summer, 25 years after the paper. Thousands of people had read that paper and nobody else had detected that it was incorrect. And it's a point for students and deans, if there were deans and people from other departments here, that I think of engineering papers, I may be wrong, but I think of engineers papers are often published in 6 months or a year or something. this was work done in the summer of 1985, and it did not appear until 1989. And this is another thing where people, when I got that result and was talking about it at different universities, they said, oh, this is going to get you tenure right away. And I got tenure in 1987, 2 years after I proved the result, but the paper didn't appear. And I was told that, this paper didn't play any role in getting tenure. So that's Hopkins. Okay, so I've really enjoyed undergraduate research. The students are very enthusiastic, very creative. They haven't read a lot of the literature and learned how to not solve the problem. And they're very enthusiastic to do things that graduate students would think is grunt work. But I've had more than a dozen different topics I've worked on undergraduates with and published on most of these with groups of undergraduates, which gives me, I have right now, I thought of this the other day and counted, I have 63 different co-authors, which is far more than I thought. When I started counting, I thought I'll count and I'll see if I have more than 30, but I have 63. The ones that are in red are the ones that I have current projects going on with students. Percolation Threshold Bounds with Sam Overly. Rendezvous Search is Drew Hendrickson. This got started with my Introduction to Research course last spring. Drew Hendrickson and Yao Zhao and Nick Parenti, who graduated, are working on that. And Counting Out Games, there's Bryce Chalheimer is working on that with me. So I'm still enjoying and expect to continue enjoying working on research with the students. The students have made us proud. This was at the Math Fest. Up until the pandemic, the Summer Math Fest conference would have undergraduate research presentation competitions with about 150 or 200 students presenting, and they'd give about 15 awards for outstanding research. And so about 10% at most awards. And every time I took students, I got at least half of my students got awards. This was 3 out of 6. Some of you may recognize some of these. So again, just like I said about Devar, I didn't screw them up as much as they thought I did. So I'm very proud that they've done so well. And a lot of these students have gone on to academia. None of my PhD students really stayed in academia, so I'm really glad that a lot of my undergraduate students have gone and done really well in academia. Okay, so now talk a little bit about the other activities at Hopkins. I was department chair for 12 years, which beats the rule that I heard, that is, you are elected department chair and you make a new enemy each year until a majority votes you out. There were 9 people in the department when I started, but I served for 12 years. So I think I did okay on that. Maybe it's just that other people didn't want to do it, which is entirely believable. But one thing that I really found satisfying was that every promotion case while I was chair was successful. And some people twice, I guess, I don't remember exact timing, but during that time, Ed and Chinaman and Jim Phil and Dan Naiman were all promoted at least once during that time. And also I was really happy that we were able to hire Carey Prieb and Don Gieman during that time. So really helped make the department what it is today. Let's see. Oh, and the other thing about being department chair was that I had 3 former chairs in the department when I started, and 2 of them did not agree with each other about things a lot. So every week, every decision I made, so essentially every week, there was at least one came in to told me I'd made the wrong decision, it was completely wrong. So when I finished, I resolved to try as much as possible to not tell chairs anything, criticize the chairs, and to only provide them advice if they actually asked me. And I think I did fairly well, but you'll have to ask Dan and Ed and Laurent and now Fadil how well I did. I may have something to add, if they ask me, but that's it. I don't want to have them have the criticism that I did. One thing that I made a big difference here, and this is on the theme of helping students, preparing students for careers, was that I founded the Entrepreneurship Management and Leadership Programs. The Center for Leadership Education is what it eventually became. When I started at Hopkins, there were no business classes for undergraduates at all, and there was no business school. And yet a lot of students wanted to go in that direction, but they would get turned down for interviews because, several students told me that they'd tried to get an interview, and the representative of the company said, well, I see you haven't taken any marketing or accounting or any business classes, and so why is this is just a last-minute decision you want to work in business, and they said, well, but there aren't any business classes at Hopkins, and the reply from the hiring people was, oh, I don't believe that. Hopkins is a very good school. Stanford and Harvard have business classes. So I started offering, hiring people to teach. I stole people from other colleges nearby that, they taught there and they got teaching awards, and I would ask them if they want to teach at Hopkins in the evening. And we got the program started, and then it got endowed by Bill Carey for $5 million after it was already, 2 years after it was already showing that it was going to be successful. And that turned out to be the test case, I guess, in some sense, that then later on Bill Carey endowed the Carey Business School. So that made a big difference, and a lot of students got to go to Wall Street and into business that wouldn't have before that. And the same thing for master's students, graduate students. I designed the Master of Science in Engineering Management Professional Master's Program as well, which some of you were advisors for and so on. So those were some of the professional development activities. And I considered the undergraduate research as helping prepare people for academic careers and see whether, test run to see whether they liked research and so on. One of the things that I had for about 10 years, I had a monthly joke contest for extra credit in my classes. And at one point in 2014, a student took a picture of one of the winners and posted it on their Facebook page, and it went viral. And in a couple hours after the class was over, my son called and said, do you know what it means to be #1 on the front page of Reddit? People from Sweden and Japan that he knew had sent, I think those were 2 places, sent him, maybe it was Korea, sent him thing, here's this joke, and he said the first time he just clicked and deleted it after he read it. He thought it was funny, but then the second time when he was looking down to the corner, he says, hey, that's Dad. It eventually was put on a math joke contest and got over 250,000 views. So that was my 15 minutes of fame in some sense. And my son played soccer for a long time. When he finished playing soccer, I wanted to see more soccer. So I went up and watched a couple of the men's games here and a couple of the women's games. And it was very clear that the men weren't very good. They're better now. But the women were really great. They played position well and played smart, and they were always going well into the national tournament, Sweet 16, Elite 8, and so on. They had a chance of going all the way to the championship. And I was going to the games. I talked to the players, talked to the parents more, actually. I was adopted as a faculty advisor about 12 years ago or so, and I give them advice on academics if they want, and maybe time management and organization, and I write letters of recommendation for them and so on. more academic advising to the parents than than the students, because the parents would be talking to me and say, well, we'd like her to switch majors from sociology to economics so she'll make more money and be able to pay off her student loans. And I'd kind of talk to them about, well, you know, she'd probably do better if she's doing something she loves. And and the player will tell me later on that, no, my parents said they had a good talk with you, and for some reason they've stopped bugging me. But they're an amazing, all along they've been an amazing group of, you know, national merit scholars, engineers, double majors, triple majors, combined bachelor's, master's. In the department, the most recent one that's, you may know that's of that type was Carey Lupton-Smith, who's gone on to a PhD biostatistics, but she was a double major and national merit scholar. And this year, they finally did go all the way, undefeated season, and won the national championship. So that was fun. And I was able to go to all but one of the 25 games, home and away. I have missed one, but streamed it on, I was at a conference and couldn't attend in person. Okay, so what next? Well, one of my former colleagues and a role model is Atchison Duncan, and he continued coming to campus and working for about 25 years after he retired until he passed away. And he, so I intend to do that sort of, you know, as long as I find it interesting and worthwhile. He, of course, did what he wanted to on his research and writing, but he, no more committee duties, paperwork, and administrivia. So, so I plan to keep doing about 60% of what I was doing before, including especially research with research with undergraduates. I've actually added an editorial board, and I've been treasurer of a small statistics society that promotes statistics in the South for about 13 years. And I've joined an executive board of an international combinatorics society. I love keeping my hands into some applied statistics by working on the enrollment prediction model and being, you know, associated with the women's soccer team. The new thing, another new thing, is the academy that's created of retired professors here on campus. They meet for lunch every Wednesday and have book discussions and discuss the news and other things. And I've got a lot of friends there now from history and writing seminars and chemistry and physics and astronomy. It's really nice. I am currently the token engineering school member. I'm the only one, and I'm not a real engineer, so it'd be nice if some other engineers join in, because I get accused of things that I'm innocent of. Okay. And so some acknowledgements. This is difficult to do because I can, you know, Amitabh in his lecture could show some pictures and so on, but after about 50 years, there's so many people. I don't want to leave people out. I can't say something about everybody, so I'm going to do it as much as possible. I'm going to do it without names. It's been an honor and a privilege to be at Hopkins for the 42 years. It's given me the support and the freedom to do a lot of things I want to do and things that I wouldn't have been able to do at other places. I don't know any other university that would have allowed a person who has never had a business course but just self-studied. My adult supervision here is okay. To start an entrepreneurship program, but it worked out pretty well. And I think that that type of freedom has to some extent gone away here. But some may think it's good, but I think there still should be some more of it, to be able to switch and do different things when you find something that you love to do and can make a difference. The department has been a great place to be. My colleagues, all my colleagues, present and past, have brought me joy in their own unique way. making it a place that I think anyone would like to be. And it's been, there's such a range of backgrounds and knowledge and opinions that it's been very entertaining. Traditionally, we've had discussions at faculty meetings and hallways that have gone on and on until we kind of reach a consensus that everybody kind of buys into, rather than just having a vote and voting certain people down. But the faculty meetings, the faculty members here will notice that I have come to all the faculty meetings since I retired, and that's one of my main sources of entertainment. Especially, notice that, and this is a career advice for the PhD students and other, but I don't want people to take my place, but I always sit at the opposite end of the table from where the department chair is, so I can hear all the banter and snide comments. And the students here have been great. Can't say more about that. My colleagues, my collaborators, I thank them for all their great ideas and enthusiastic conversations and help, and for their patience and tolerance with all my revisions, which lead to the joke that I now use, that keep revising. We always keep revising a paper until it's had at least 17 drafts before it gets submitted. And then finally, my wife, Susan, the one name I mentioned, I guess, that I married the smartest girl in my high school. And for over 51 years, she's given me love and adult supervision. So thank you all for listening. Thank you all for coming here. Thanks to the enormous audience online. And I've given my email and office so that if you want to hear more stories about research or the university or whatever that I'm not willing to tell in public, contact me and we can get together. So thank you all. I stay up here? Wait.
John, thank you. Congratulations on your retirement and for your service and inspiration to the university. It's a different place thanks to you. We have a...
You didn't say better, but...
Absolutely better. Absolutely.
Wonderful.
Look at the camera.
Look at the camera and say me.
All right.
Wonderful.
Thank you very much. One more round of applause for John.
Thanks to you.
And we have some refreshments. Please stay and enjoy.
Great. Wonderful. Thanks.